gets me into trouble at various times. My wife can hear everything I say when I'm in the building at UC Santa Cruz, and she makes sure that I work. Okay, so I guess we have to turn this on. Big question. Big question. How do things move, right? And so we're focused here on axonal transport, neurodegenerative disease, relationships. But I think it's instructive to think about lots of different motility processes. Am I in the way? Okay. You can read it right here. There. We're fine. Okay, I'll behave now. You want me to stand in a particular place here? Right here? This will not work out. How do things move? Okay, so we've been focused on axonal transport. I encourage you to look at many different motility processes. They are fascinating and I think instructive. So here's what we've been studying, talking about, lecturing about for the last 8 days, 9 days. Mitochondria moving into soft axon. So axonal transport, this is saltatory. Things move in a stop and go fashion, back and forth. Individual organelles moving independently of one another. And so then what I'd like to talk to you about today is a different process in which you have a general flow of the cytoplasm. All right, so cytoplasmic streaming. Yeah, Jen? What? Oh, the lights? I don't know. You want me to use the microphone? You guys keep controlling the every direction. There must be a light switch here somewhere. Okay, come to order. That's a problem. We have a new problem. Oh, that's on. It just will take a minute to warm up now. What can I extemporize about? Do you really need this microphone? Okay. Oh, but you need this for the recording? Is that? No. Okay. I forget about all these things. So what I'm going to try to convince you is that the behavior of these individual cargos that are being moved by motors along microtubules, if they behave in a concerted fashion, they will generate a bulk flow of the fluid that surrounds them. It's intuitively simple. There's viscous drag on the individual particles, and if they are moving in a cooperative manner, you can get generalized flow. And the generalized flow is something that we should think about because it's a way for motors to transfer force to other objects that are at a distance from themselves. They don't have to be physically connected by biochemical linkages. All right, now we are going. So the background for all of this you have had plenty of recently. Filaments, motors, microtubules, microfilaments, various motors, motor-associated proteins, filament-associated proteins, cargos, and the organization of the filaments has great influences on the way the mechanisms, on the outcome of these mechanisms of motility, how force is directed. So here we have in the axon, which now we're all familiar with, minus ends toward the cell body, plus ends towards the terminal, and bidirectional individual movement of these organelles. Okay, so now here's the oocyte, and we won't now go back to axons anymore. The oocyte, can you see this well enough? Yes. All right, so in the oocyte, Drosophila generates oocytes in an assembly line. Up here, there's a stem cell that divides and produces a germline precursor, and that divides another 4 times to produce 16 cells. And of those 16 cells, one of them wins and gets to become the oocyte. The other 15 are slaves. Slaves that feed the oocyte materials. They generate massive amounts of cytoplasmic components, and they feed the oocyte with those components to build it. They do this through cytoplasmic bridges because cytokinesis during those divisions was not complete. All right, so there are cytoplasmic channels between all these cells. There are 4 channels that go from these nerve cells into the oocyte. As the egg chamber matures, the oocyte grows, the whole thing grows, but the oocyte grows more than the rest. These stages have numbers. You'll see this number appear at various times. This is about stage 9. Okay, nerve cells, oocyte, follicle cells around the edge. Here's a cartoon of the same thing with the channels. All right, scale. It's about 150 to 200 microns wide, 200 to 300 microns long. Microtubule organization and microfilament organization. Minus ends and microtubules are, we think, anchored at the cortex on the periphery. So this is backward from the classical cell with a stellate array of microtubules emanating from a microtubule organizing center. In this case, the microtubule nucleating capacity is mostly in the cortex of the oocyte. And so the plus ends point inward. The cortex, this purple area, is a dense meshwork of F-actin filaments a few microns thick. And there are also F-actin filaments that run throughout the cytoplasm. But they're not as dense. Okay, so what is going on in here? Well, there are a variety of different motility processes. One of them, a number of them are designed to polarize the oocyte, producing the future body axis. So which end is the head, which end is the tail? What you see here is messenger RNA. These are in situ hybridization. Messenger RNA for bicoid has been localized in a microtubule-dependent fashion to the anterior. Oscar messenger RNA is localized in the posterior. This signals build the germline here, and it also does some signaling for this is the posterior. So during, you have to think about, so these mRNAs form large particles, and they are transported in a saltatory manner around in the oocyte to achieve these positions. It's a slow process. It happens over the period of 8 to 12 hours. And so this microtubule organization, it looks all higgledy-piggledy, and it is. There's a slight bias of more minus ends here and more plus ends away from here. And so dynein helps get this up here. Kinesin 1 helps get this down here. Right? All of this jostling and saltatory transport going on during these early stages up until stage 10B. Now, have I forgotten something? Yes. So, after this, the nerve cells are feeding in mRNAs bit by bit. The mRNAs are getting delivered, and they're also feeding in mitochondria and all the other components of cytoplasm. At stage 10A, which is just after this stage, all of a sudden the nerve cells start to contract. And they squeeze their cytoplasm in bulk, not just bit by bit. In bulk, there's a flow of cytoplasm that goes through these ring canals down into the oocyte. That cytoplasm is different from the early cytoplasm of the oocyte. And during that, it's called dumping, cytoplasmic dumping into the oocyte. These things shrink, this thing grows. There's a need to mix the two qualitatively different types of otoplasm. So this is the early stage, stage 9. And keep in mind that the time scale here is compressed a great deal. And so you have this sort of churning that's going on during the early stages when Oscar is getting localized here. Bigfoot is getting localized. Here's the nucleus of the oocyte over here. And then at the 10A, 10B transition, yes? I forgot to say that. These are yolk particles, and they are autofluorescent. And so in the early days, we just use the fluorescence microscope, and if you set it up especially, you can get images of the yolk granules moving. But it's much brighter if you inject the abdomen of the female with trypan blue, fluoresces in many different wavelengths, and fluorescein. Mario Quinlan has started injecting fluorescein. That works quite well. So the way yolk gets into the oocyte is that it's generated in the body, and then it's transported through the hemolymph in the circulatory system, and then it's endocytosed by the oocyte. And so when they endocytose the yolk particle, they take up the dye that makes the yolk particle nice and bright. Okay, so the drama here is going from this state to this state. We think that this concerted flow is very important for mixing the oocytes. The incoming, you can see the incoming clear. So yolk doesn't come out of the nerve cells, right? It comes laterally from the hemolymph. So you can see clear cytoplasm, yolk-free cytoplasm coming in up here, and it's getting stirred in.
For this also done with the oocyte by analysis, apart from proteins and RNAs, organs are also coming in the oocytes.
Everything is coming. Everything except the nuclei. Everything gets squeezed. Maybe I'm not understanding the question. Are you asking me what comes in with the dumping?
Yeah.
Okay, everything. All of the cytoplasm of the nerve cells gets dumped into the oocyte.
Including the MTOC?
MTOCs, I don't know. Well, I think there's I think most of the MTOCs come in early into the oocyte, out of the nerve cells. And they collect first at the posterior, and then they kind of degenerate. And people for a long time thought they disappeared. But now there's more recent evidence that some of them survive and actually hang around the nucleus. It's a point of confusion. What happens to the MTOC? So go back to the. So is there? So actually, this was done in Santa Cruz, California, in the northern hemisphere. If we move to Australia, then they go the other way. No, there is no pattern. And this one looks. If you look down here, you can see it develops a chaotic change. I can't say chaos. Tom is here, he knows what chaos is. But it has a profound variation in pattern that happens. Sometimes you'll have two vortices, sometimes it will stop and move the other way.
This actually reminds me of paper last year, in which what they do is they use kinetics, timers, and mitochondrial, and they show that if they confine this solution of nitrogen and timer, and there is spontaneous flow.
Yeah, so it's Sanchez et al.
Yes.
And it was in Science?
Science.
Okay. And we can talk about them in a while, but that could get into a long discussion, so we'll wait. But I think the same principles that drive this cytoplasmic streaming are also driving the wiggling of those microtubule bundles that Sanchez reported. Can you see Julie okay? Okay. Okay, so what's going on here? So what is required for this process? First of all, if you apply colchicine, which will compromise microtubules, both of these motility processes stop. Okay, so they need microtubules. If you apply cytoplasmin, which depolymerizes F-actin, then this process, this vigorous streaming process, actually occurs during this period. And you can do that genetically also by messing with actin nucleating proteins and things, captain inspired. And so what the result is then all the careful patterning of the mRNAs gets disrupted because they get swept off their anchor points, and you get an oocyte that has no, you get an egg and an embryo that has no polarity because it hasn't been patterned properly. So controlling this transition, timing it relative to the patterning of the oocyte, and then getting it done to get the mixing is quite important. Okay? Now here is what happens when one eliminates kinesin. And what happens is that it, like microtubule depolymerization, kinesin knockdown stops both processes. So kinesin, we think, is generating the force that drives this. It's generating the force that drives this. You can see here the clear cytoplasm that's flooding in from dumping, has no yolk endosomes. You also see some jiggling here, which I think is probably actin-myosin-based movement. And if we take frame rates very fast during this process and slow down the time lapse, you can see that actually the path of each particle is jiggly like that. So it's sort of a compound movement. All right. Kinesin heavy chain. Okay, so what about dyning? So, what do you expect will happen when we knock down dyning? Someone yell. You don't think it will move anymore? It moves the other direction. We'll go backwards. Well, the surprising thing is that what happens is that after the injection of antibody that's inhibiting dynein, this stage 9 oocyte, which is doing slow streaming, will start doing fast streaming. So dynein is resisting the force generated, the uniform force generated by kinesin that drives the streaming process. Okay, so it's just like knocking down F-actin with cytoplasmic. Jim, do I see this? Oh, another approach to inhibit dynein? Dynein knockdown prevents the development of the egg chamber. So that has been difficult. We did alternative approaches by using different antibodies. We did dynein intermediate chain, dynein heavy chain. They both do this. Dynactin, interestingly enough, P150 glued antibody does not influence this process. Recently, Grady and Gonsalves have been working with a fast induction of siRNA, of hairpin RNAs, to knock down dynein, and he gets similar results. Say it again? Ciliobrevin? This is a drug? Huh. All right, I'll try that. I won't try it, but the students will. Try it again. Why use the antibody instead of a mutant? Because a mutant kills mitosis, and you never get from the stem cell to the full oocyte. It stops development. Dynein is so important for so many processes that you can't do without it. Kinesin 1, the oocyte doesn't care. It develops, everything's fine until you get to the processes of mRNA localization and streaming. Kinesin 2 mutants we did look at and had no effect. We looked at myosin 5 mutants, no effect. We looked at Milton mutants, no effect. And some other ones.
But there's a recent paper which talks about the myosin 5 role in the transport of Oscar mRNA towards the posterior.
There is. And so it may well have something to do with either transport or anchorage of the mRNA particles at their proper location. But not streaming. We tried to experiment a few times and get no results, so we stopped. Maybe if we pushed harder, we would see some effect. Sanja? Oscar goes to the posterior. So the orientation of the microtubules is minus ends anchored at the cortex. That's a debatable opinion, but I think it's well substantiated. Plus ends are wherever. Okay? But there's a higher concentration of minus ends at the anterior. The microtubules are more dense at the anterior. And so this creates a bias in where the plus ends are. So there's more minus ends at the anterior, there's more plus ends away from the anterior. And St. Johnson's group has done particle tracking of Oscar now, and it moves in a very saltatory fashion, and it follows a biased random walk that over 8 hours gives you a concentration of Oscar at the posterior. Not all of the Oscar in the oocyte is at the posterior. It's about a 3- or 4-fold enhanced concentration at the posterior. And these in situs, they give you a bias too. It looks like all of it's there, but it's not true. It's just an increased concentration there.
There must also be anchoring molecules for Oscar.
Yes, there are anchoring molecules, including Oscar protein itself.
Maybe you can hold the questions for 50, because we have 3 minutes, and I don't know if
Okay, let's go. Okay. So, slow streaming, you need microtubules, kinesin, actin, dynein, fast streaming, you need microtubules and kinesin. This is a wonderful thing, because now we have a motility process that is simplified, and we don't have so many components to deal with. To me, anyway, it seems like a wonderful thing, so we can start to think about how it all works. Now this, is going to show you microtubule behavior during these streaming processes. And this is stage 9, and this is after fast streaming starts, GFP tubulin expressed just in the germline cells. Okay, these are wild type. So, slow streaming, you can see, you can't see single microtubules very well. You get the impression that there's a meshwork. And these things have some areas in which there's some parallel alignment, but they're quite small, those areas. When you convert to fast streaming, you have a dramatic alignment of the microtubules that varies over time. The directions of the parallel arrays change. You can't say rapidly because this is, again, 225 times sped up. But they are parallel, they are organized better, and they seem to point in the directions in which the cytoplasm flows.
So the question, when you use some other cell, some smaller cell, would you see this cytoplasm?
If we have a small cell, well, you can induce this in stage 8 or stage 9 by knocking down actin. So it's smaller, but it's not a small cell. I haven't heard of small cells that do this. Size would be an interesting part of the model. Yeah. Okay, so here's a different way to look at it. This is with the multi-photon scope, and this is slowed down now to 45 times real speed. And you can see this more, now it's more majestic. This is still faster than real time, right? And what we have here is a curved surface that has been flattened against a piece of glass, cover slip, and so it's wrinkled. And here, right here, you're in the cortex, and the yolk particles that are there, yolk particles are now dark and negative relief. The yolk particles move very slowly or not at all. They're trapped in the cortex, associated with the cortex. Here, the focal plane is beneath that layer, and you can see the microtubules undulating down there along the flow. And then the final microtubule behavior here is with the spinning disc scope at higher magnification. And you can see the individual, bundles of microtubules and the way they behave. They curve, they bend, and the bends propagate toward what we think are the plus ends of the microtubules. The tubulin is a fusion with GFP, and it's expressed in the germline cells.
So what initiates the stream?
What initiates the fast streaming?
So from stage 9 to stage 10, what happens?
That's a good question, and it's one I would love to answer. And I'll try to convince you that we are onto something here. All right, but that will be at the end. Well, they're roughly parallel, yes. We think so.
So, I mean, if I go back to that paper, so they said that this kind of scheme required anti-parallel.
That's nonsense. They're wrong. Why do I think that? Because we've tried to model the anti-parallel arrangement in their microtubule bundles that wave. It does not work. That was a hypothesis that they had anti-parallel things and kinesin, multivalent kinesins tugging things in different directions, and that produced the wiggle. But they did no modeling. And if you do the modeling, it doesn't work. But we have an explanation for it that does work. Yeah, we can talk about that in a minute. Okay, so here we have the intuitive model is that during slow streaming you have dynein and kinesin moving on microtubules in different directions. And it can help create disorder in the microtubules. There's a high viscosity cytoplasm with F-actin filaments throughout. To switch to fast streaming, you knock down some of the F-actin, reduce the viscosity. You allow kinesin to run toward plus ends, unhindered by dynein activity. And so you get a push, a uniform push from each moving object toward the plus ends of microtubules. That causes the concerted motion drags fluid along, and the fluid becomes a coherent flow. So that's the intuitive model. So now, let's talk about the microtubule bending, because we have to explain both the bending, which kinesin drives, and the fluid flow, which kinesin drives. So, can kinesin move fluid? Well, if it's moving this object, the object has frictional interactions with the fluid. As the object moves, those frictional interactions move some fluid with it. At the same time, Newton's third law says that the kinesin is generating force on the microtubule going the other way. And so the microtubule will move this way. The object the kinesin is carrying will move that way. And you cannot generate long-range concerted fluid movement in that fashion, because the fluid motion generated by the microtubule and by the kinesin at distances that are some distance away from the tube will cancel one another. Okay? That's Newton. Does the degree of cross-linking of the actin matter? It probably does, but we haven't. Say it again. So the cross-linking of the actin filaments will define viscosity of the solution, and that will definitely influence the way the mechanism works. And so,
this manifestation that flows that John wants to make to disrupt the outside language.
alpha actin. The spectrum, sorry, alpha spectrum. I don't remember this. But so the actin is very important in anchoring things to the cortex, and we think it's important for controlling viscosity of the cytoplasm, which in turn has an important effect on the mechanism. Okay, so we cannot generate fluid movement in this fashion because the microtubule moves one way, the cargo moves the other way, they cancel one another out. But if you can anchor the minus end of the microtubule so that it cannot move, then when the kinesin moves forward, what happens? Then you have bending. So the microtubule will bend because the minus end can't move. Okay, simple concept.
But the dynein can do the same, and when they are moving towards negative direction, microtubules move towards the positive direction.
So if dynein is in effect here, dynein would be moving this organelle this way, force on the microtubule is this way, it would tend to straighten the microtubule. if the minus end is anchored. You could make this system work with dynees if you anchored the plus end to the cortex and left the minus end free.
No, because I want to know whether dynees can also cause bending of microtubules.
Not if the minus end is anchored, because then it's pulling on it.
It's just free.
Oh, if it's free, if the microtubule is free, well, the microtubule will slide, just like in a gliding acid. Right. So either way, it works the same. Okay, so Susan is going to shut us down, so we need to proceed here. So he's tough. This question of are the minus ends of the microtubules anchored? It's very important. Okay, so there was a paper from Long and Reitman in which they saw a shift of, this is with immunofluorescence, they saw a shift of staining anti-gamma-tubulin and anti-alpha-tubulin staining away from the cortex centripetally by a few microns at the transition from slow to fast screening. And so they think that the microtubules are released by the cortex and then they flow with the cytoplasmic flow. We and Isaac Newton think that that's not possible. If the microtubules, I consulted him, then you can't, that won't work. But we went in to test it. And so photobleacher region, this is just subcortical. This is fuzzy, but it's because we went into high mag. Subcortical photobleach, if the microtubules are flowing, that photobleach dark zone should move. All right, so here's the experiment. Now it's frustratingly quick recovery. You don't really see the thing move, right? But the streaming is moving through here. It takes about 30 seconds for an object to move across this 10 micron space. And there is probably a lot of free tubulin, and there may be some free microtubules also. So what we have done here is traced intensity across this direction, and you see the intensity recovers. If you mark the central minimum at time 0, and then at time 15 seconds, if the microtubules were moving with streaming, they should move 3 to 4 microns in that 15 seconds. They don't. So we think that these microtubules are anchored, or at least a substantial population of microtubules is anchored. There probably are some that are free floating also. The rates of, the rate of recovery doesn't depend on actin. I don't know. I never wondered that.
But you know that we use cytoplasmic D and
cytoplasmic D makes streaming go early and fast. So, yes?
What are these organelles which can be of
These are yolk granules.
and some of the, so the ones where the microtubule or the streaming is happening, they move quite fast in that area. The rest is.
These are trapped in the cortex, and this is close to the cover slip, and there's a wrinkle. So there's a wrinkle, and this gives us a deeper view. So we're seeing just below those stationary organelles in this region. So it's a subcortical layer of microtubules. How is the microtubule anchored? By its minus end. I do not know. Okay, so how does a moving object move fluid? By viscous drag. Go ahead. So there is, people have measured the elastic constant of microtubules, and I don't remember the exact numbers. 24, no, I can't remember.
So, sir, we are seeing a lot of bending factors.
Yeah.
It is because of those are very massive, just like one way of being something. Because there are a lot of bending factors. Can those might be just like doing the other one.
I will show you bending in a minute, okay? Some simulation of bending. But first let's talk about how fluid moves. So how much fluid can this lipid droplet or vesicle, how much fluid can it move? Well, close to the moving object, the fluid moves at the rate of the moving object. But as you move away, the velocity decreases as 1 over the radius. Okay, so it drops off quite quickly. These are little arrowheads out here, so there's still some movement, but it's tiny. You get about a diameter of 1 to 2 diameters of the moving object, you get substantial fluid movement. Now, that doesn't look like very much. How can we move the whole cytoplasm of the oocyte? Well, if you, instead of having a sphere, if you have a rod of the same diameter, you can move a lot of fluid. Because, and the easiest way to think about it is that the frictional interaction between the moving object and the fluid is dependent on the surface area, right? So a rod has a great deal of surface area, and at these low Reynolds numbers, it doesn't matter if the rod is moving sideways or moving the long way. It's the same frictional interaction, all right? So if you move the rod the long way, it can move a substantial amount of fluid. Or if you're thinking about a microtubule, the microtubule itself moving could move a lot of fluid. Or if you line up a whole bunch of organelles along the microtubule, it's acting like a rod. So this rod-like array of vesicles moving along the microtubule, now instead of one diameter, having movement 1 diameter away, you can go almost off the chart here, and you have massive amounts of fluid moving. Okay, so the rate at which velocity drops off here is less dependent on the distance from the moving object. Yes, and so it's just like we said with the microtubule and the organelle. If you have opposing motion, they cancel. And so you have to have that minus n anchor in this case. Yeah, if you have organelles moving in the minus direction, that will screw things up, and so maybe that's why we have to have an inhibition of dynein to get fast screening. Okay, so the amount of fluid that array, that rod-like array of organelles can move is actually equivalent to a sphere of that diameter. And so it's really quite an efficient way to move fluid if you have a long linear array along the microtubule of repeated organelles. And things that influence this are the spacing between the organelles and the diameter of the organelles. Okay, so closer spacing, you get more rod-like behavior. Larger diameter, you get more surface area, and you get more movement too. Let's see. Okay, so there's one more riff I want to do here. If you use 250 nanometer diameter lipid droplet, it's a big vesicle, which is a common thing in the oocyte. To get the velocity of streaming that we get, which is about 1/4 of a micron a second, from the movement of kinesin, which is about a micron a second, you need to space the lipid droplets about 1 micron apart to get that profile of fluid velocities. If you go to a small vesicle, 40 nanometers, 50 nanometers, then you need to space them about 150 nanometers apart, 150 to 200 nanometers. And so you can reduce this down. And the smaller the object that moves on the microtubule, the closer the packing needs to be. So if you take that to the ridiculous extreme, how about just kinesin by itself with no carbon? And it turns out with a 35, if the stalk of kinesin is a rod that's basically 35, 40 nanometers sticking out from the microtubule, if you put them about 100 nanometers apart, that would be a very effective fluid moving situation. And so that's kind of interesting. Yes?
Without Parkinson, it's like more like 85.
85. Okay. It's like the whole microtubule. If you have the surface of the microtubule coated with kinesins and they're moving, it's like the microtubule's moving. It's a long rod. It's a huge fluid mover.
So the main force for the mixing is the microtubule acting like a copycat, right?
No. No. Well, the vesicle or whatever is pushing on the fluid is moving fluid towards the plus end, and the balancing force on the microtubule is causing the microtubule to bend, and the bending does influence fluid around it, but it isn't the propelling force. Okay? Yeah, and think at low Reynolds number, you cannot move anything except if you push on it directly. So there is no turbulence, there are no vortices or eddies that go on. As soon as you stop pushing on something, it stops moving within 1 hydrogen atom diameter. So you have to push all the time to move things.
So Bill, I'm also confused. So are you saying that the kinesin binding to the vesicle is creating a flow that's moving the other vesicles, or are you really saying that the kinesin alone is moving and creating a flow that's moving all the vesicles?
It can be either way. So the kinesin by itself would generate fluid movement that would then carry vesicles that were not anchored to the filaments themselves. Carry them with the fluid. Or kinesin hooked to a vesicle can push fluid, and other vesicles or yolk granules that are surrounding it would move with the fluid, because the force is transferred from the motor to the fluid, and the fluid transfers force to the moving object.
So is there any evidence that there is different kinds of movement dynamics in the liquids? For example, if you have a portion of vesicles that are actually binding to kinesin and moving, and then you have another fraction of vesicle that's being carried by the track, you would expect that you have two different, very different kinds of orders of magnitude differences in the active velocity.
So, yes, and so the difference in velocity between the actual object that's being carried along the microtubule at roughly 1 micron per second and the neighboring fluid drops off as a function of 1 over the radius. Okay? But the radius of a whole platoon of objects moving along a single microtubule, the effective radius is huge. The effective radius is as long as that platoon is. It's like a sphere that's that big. And so the drop off in velocity as you move away from the microtubule is quite slow.
So is there evidence that there is a variety of velocity rates which actually measure the velocity of these different vesicles?
No. Well, yes. There are different velocities, but we think it's because they're in different fields where there are dense packed microtubules in some areas and less parallel arrays of microtubules in other areas. And I think that's what the variation is. Within any one region that has a parallel array of microtubules, we think the fluid velocity is uniform. And it's because the microtubules are so close together that the fluid field that each generates is interacting with the others, and they collaboratively get this 0.25 microns per second out of the 1 micron a second for the kinesin.
go random, will you generate less?
Yes. So a smaller organelle generates less drag and less force and less movement. How do we get to directionality? You have a whole bunch of small objects moving all in the same direction. Oh, no. The microtubules move with the flow, right? So the flow works on the microtubules, which is what I'm going to show you right here. Okay, so, John.
So I have a similar question. So in that, the diagram you showed, you basically had an infinite width on which you're trying to exert this fluid flow, right?
Oh, you mean in the tensor diagram?
Yeah. But you clearly had like a maximum stream size in the earlier movies you showed. So if you constrain it more, does that give you completely different numbers?
Different numbers in terms of these vectors out here?
You should get much faster flow.
Well, sure. And so in reality, what we have is a microtubule here, and a microtubule here, and a microtubule here. They each generate this field of vectors, and they influence one another and cooperatively help one another generate a uniform flow field.
So I suppose that we have to go down to the question, and we have to get out and keep.
Okay, well, we will hurry now. I'm almost finished. Okay, so modeling. So my friends, Matt Bruner and Josh Deutsch, biophysicists at UC Santa Cruz, I talked to them about my ideas about this, and I've done this for like 10 years. I've talked to people, physicists, and gotten them excited about this, and then I say, well, let's do some math, and they would uniformly say, I gotta go. But Josh Deutsch said, okay, and he came back 2 days later, and he had a manuscript written that had the mathematical relationships put in it. So here what we have is, I shouldn't have started that yet. Okay, so just look at it. This is microtubule-like filament, all right? And it is 1,000 times the actual diameter of a microtubule, just so that we can see it, all right? So it's not really that fat. And this distance is about 80 microns across here. I'll start over again. So what we have is the minus n fixed in space. It sits out in open space. And you have a randomized coil to start with. The computer randomizes the positions of the segments. And there is on each segment of the microtubule-like filament a force that is pushing back towards the minus n. That's the kinesin-like force that we think is going to tend to make it bend. And what else? We impose a flow field in this direction to be like a fluid flow field so that you can think about how it works. And so this is what happens. It generates this helical wave that propagates toward the plus n. The radius here is about 40 nanometers. No, 40 microns, sorry, 40 microns, the radius. And, well, it looks more like 80 microns. Oh, the radius is about 40, right. So flow field that way, anchored minus n. This was a startling result. Josh was very excited. He didn't think anybody had seen this before. And what it gave us was a way to think about how the bends, so it does, kinesin can generate these bends. They can generate a stable helical wave. The rate at which these waves travel towards the plus n matches the rate at which waves of curves, the curves in the microtubules in the oocyte move along in the cytoplasm. The radius of the bends in the oocyte is roughly similar I mean, it's about 20 microns here. We're looking at 40 microns, but the variance is substantial. So we're in the right ballpark. And now, so we were excited about this. And my colleague, Bill Sullivan, came in and looked at us being excited, and he said we were stupid. He said, this doesn't look anything like an oocyte. What are you talking about? And so it made us rethink it and think, okay, so this filament and the forceps have to generate their own fluid flow field. And you have to have more than one filament. And so what Matt did for his thesis was to put 100 filaments, randomize their starting positions. They are now anchored to or just above a barrier that's in the background. So that's like the oocyte cortex, the oocyte plasmameria. And let's see, the same tangent forces on the microtubule by kinesin, but then an opposite force on the fluid that's toward the plus ends. Can it generate the bending behavior of the microtubules? And in fact, no. You get some mild areas of correlated behavior in here, but not the kind of behavior that we get out of the parallel arrays and fast streaming. So what's going on? Matt went back to his computer. Each of these simulations takes a couple of weeks. He went back and tested for months, varying different parameters, spacing of the minus ends, the distance between the minus ends and the cortex, stiffness of microtubules, force generated by kinesin, things like that. And he eventually found that there is a space, there's a parameter space in which things do work. So the only difference from that last simulation and this one is that now the minus ends, instead of being this high above the cortex, are now double the height. So there can be fluid flow underneath the point of bending, the initial point of bending. And so this is what happened. And so now it works. And you can mess with other parameters. One of them that matters is the force generated by kinesin on these filaments. If it's too high, they behave in that semi-chaotic manner. And one way to reduce the kinesin-generated force on those filaments is to reduce the viscosity of the solution. And you can do that by reducing F-active concentration. So maybe
It's not effective, you mentioned the increases the fast speed. So,
yeah.
this will suggest that they have to be anchored at a certain region.
That they have to be 2x above the, so the 2x means twice the spacing between minus ends. And so this issue of how do you anchor a microtubule in space so that fluid can flow under it, that's a major thing that we have to figure out. So it could be that the stationary granules provide some space, and then that helps stiffen the base of the microtubule, and the microtubule has stiffness, so there is some space beneath that initial segment that's parallel to the cortex so you get flow. But you have to have flow all around the microtubule to get the correlated with one another. All right, so Sujit are almost done. Okay, so here, now you can just go back. We think that we are on the right track with this modeling system, and now we have to go in and do some hardcore electron microscopy, look at the organization of these microtubules in the cortex, try to figure out the spacing of cargos along the microtubules. We're trying to figure out what linkers are active, linking kinesin to cargos, cargo identity, all the biologically important ways to test the mechanism. Everybody wants to know about this one. This isn't. Matt tried to put in particles that would show the fluid flowing because the fluid is flowing here, but we can't see it. And so he threw in an equation one day and it turned into a microtubule and it flies off. So it didn't. Okay. So here is, these are some of the people, and that's Santa Cruz with the ocean in the background. It's a nice place. We got funding from NIH and University of California. And here's a shout out to Krishanu, Lee, Seema, all the other people who have made this all happen. Thank you very much for inviting me.
So the state of the